All right, in this video, we're going to show how to find centers of mass and moments in cases where we have an infinite number of points in the set, rather than just a finite group that we can add up. So as you might guess, calculus is going to be involved here. Okay, so here is a region in the plane, which is defined above by the function y equals f of x. It's defined on the left and on the right by specific x values, x equals a and x equals b, and it's defined below by the x-axis. So this is a region that we're relatively familiar with now, having gone through most of a semester or most of a quarter of calculus talking about these. So what I'm going to do is I'm going to try to find the center of mass of this object. In order to do that, I need to be able to figure out how to find the center of mass of an infinite number of points. And the way that I'm going to do this is with a nice shortcut. It turns out that if you have an object that has symmetric properties, you can guarantee certain things about its center of mass. So for example, let's say that you take a circle. If this circle is completely filled with material here, so we have a circular laminate, right, a flat disc here that has some weight to it, the center of mass is guaranteed to be right at the center, as long as all the mass is distributed evenly, right? As long as the density is the same everywhere. So we're going to assume here that we have constant density. So whenever we have nice symmetric properties, we can tell a lot about the centroids of these shapes. So for example, if you had a hexagon, try to get this roughly accurate here. So imagine this is a regular hexagon. Once again, we have a nice symmetric property to hexagons. If you draw a line from one end to the other, point to point, you'll cut that hexagon exactly in half. The left side and the right side here are exact copies of one another. So if the density is the same everywhere, then the mass on the left and the right will be the same everywhere, meaning that the center of mass must be somewhere on this line. That same thing is true, however, if I divide the thing up this way, right? So the center of mass must be on each one of these lines, therefore the center of mass has to be right here. Again, the center of the figure. So there are lots of figures where we can figure out the center of mass by symmetric properties. One really important one is the rectangle. If you have a rectangle, you can guarantee that the center of mass is exactly in the center here, halfway between the left and the right sides, halfway between the top and the bottom. So we're going to use this fact now, this last fact here, to try and figure out the centroid and the moment of this whole shape. We know that if you can break your system up into a finite number of pieces and find the moment of each one of those pieces, you can add up all of those moments to find the total moment. So what I'm going to do is I'm going to break this up into a bunch of pieces. This part should feel pretty familiar. Pretty familiar at this point. We're going to break up the interval here into a bunch of subintervals. Let's say that there are n equal size subintervals here with a width of delta x. For each one of them, there's n total. So we have x1, x2, x3, all the way up to xn on the end here. And we're going to split this region up into a bunch of vertical strips. And then we are going to approximate each of these strips with a rectangle. Okay, so how are we going to decide which rectangle to use? Well, nice thing about centroids here is that they are based around what's essentially the midpoint. So I'm going to use the midpoint rule to set the height of each of these rectangles. Take the middle of each of these subintervals, and that's going to define your rectangle. Take the middle, that one defines your rectangle. Take the middle, that one defines your rectangle. Same thing all the way through here. All the way through. So we have all of these different midpoint rule approximations for each of these subintervals here. And so for a particular one of these, we are going to find the centroid. Okay, well, let's say that right here, This is x sub I bar. That's our notation for the middle point in the ith subinterval here. So the bar tells me that it's the midpoint. Okay, where is the centroid of this particular shape? Well, because it's a rectangle, it's going to be exactly halfway between the left side and the right side. So it's going to be somewhere above xi bar. And it's also going to be halfway between the top and the bottom. So it's going to be exactly halfway up this rectangle, meaning that the height here is going to be exactly half the height of the rectangle. Well, the height of this rectangle from here to there is f of xi bar, right? That's just the function evaluated at xi bar there. That's exactly how tall the rectangle is. So the centroid here has a y-coordinate which is exactly half of this. That means that our centroid, our ith centroid, ci, is going to be at the point xi bar in the x direction, and then 1/2 f of xi bar in the y direction. So there we go. These are the coordinates of the centroid of each of these subdivision rectangles. So now you can find the moment of each of the rectangles here by imagining that all of the mass of the entire rectangle had been concentrated at each of these points. So we are going to get a bunch of different point masses. Here, then approximately here, I guess, then a little bit higher, then a little bit lower again, lower yet, lower there, again lower, a little bit higher, and a bit higher. So each of these orange dots is now the centroid of one of these different subintervals here. Imagine now that we had I number of point masses, each at these positions. So 3, 4, 5, all the way up to n at the end. Right? We have n different point masses here. So how much mass is in each one of these? If we can figure out how much mass is in each one of these rectangles, then we know their location. We can find their moments with respect to the x-axis, to the x-axis and to the y-axis here. So how much mass is in one of these rectangles? Well, we assumed that there was a constant density here. So we're going to call that density rho. This is the Greek letter rho for the R sound. It's the standard letter used to describe the density here. So the mass of this shape is going to be the area times the density. And we're talking about the mass of an area now. So if we can take this density and multiply by the area of this shape, we'll be good. So what is the area of this shape? Well, it's a rectangle. So we take base times height. The base is going to be exactly delta x, and the height is going to be f of xi bar at each point. So the mass, mi, the mass of the individual piece, the ith piece here, is going to be found by taking rho times the height of the function here, f of xi bar, times delta x. That is going to be the mass of that individual piece there. So now I can find the moment with respect to each of the axes. The moment with respect to the x-axis, what I'm going to do is I'm going to take the mass times the distance away from the x-axis that point has. So the moment with respect to the x-axis is going to be rho times f of xi bar times delta x, multiplied by this vertical distance here, the distance of each of these points from the x-axis there. That's going to be the distance that I use for my moment calculation. So we're going to have rho times f of xi bar times delta x, all multiplied by this height here, which is 1/2 f of xi bar. And so if I reorganize this, factor the 1/2 out front, f of xi bar times f of xi bar is going to be f of xi bar squared. We are going to have 1/2 rho times f of xi bar, the quantity squared, times our delta x. Okay, there's the moment with respect to the x-axis, the moment with respect to the y-axis, my. We're going to take this mass and we're going to multiply by the x-coordinate of the centroid, which is just xi bar. So we're going to take this rho times f of xi bar times delta x and multiply it by another xi bar. So again, if you reorganize this to be a little bit neater, we usually write rho times xi bar times f of xi bar times delta x. Okay, so far so good. We now have an expression for the mass, for the moment of each individual one of these bars, right? I should not use that word. Each individual one of these rectangles here, we have a moment with respect to the x-axis and with respect to the y-axis. So if we want to find the moment of the entire system, all I have to do is add up each of these, and that will find the total moment. This should really have been I in each one of these cases, because this is an individual moment. Okay, so now let's calculate the total moment of the system. We're going to add up the moments with respect to x to find the total moment with respect to x. And same for the y value there. So the total moment with respect to x is now going to be the summation from I equals 1 to n of this expression right here. 1/2 rho times f of xi bar squared times delta x. 1/2 rho times f of xi bar, quantity squared, delta x, and the total moment with respect to the y-axis will be the summation from I equals 1 to n of this expression, rho times xi bar times f of xi bar times delta x. Okay, so now we have the moment of the entire system. This is good news, right? We're doing great at this point. In order now to find the centroid, we need to take each of these moments and we need to divide it by the total amount of mass in the system. Well, how much total mass is in the system? That's going to be the mass of each one of these bars all together, right? That is just the density rho times the total area of this shape. Right? I don't need to actually calculate each individual one and add them up. I know that the total mass of this system will be the total area times rho. Or in other words, m is equal to the integral from a to b of f of x dx, all multiplied by rho on the outside. And so in order to find the centroid, I am going to take these guys and divide by this one. But first I need to make them precise, right? Sorry, I forgot that step. Excuse me for a moment here. These are still approximations because we haven't applied a limit. Take a step back here for a moment. Sorry about that. These are still approximations because each one of these rectangles is only an approximation of the actual area of the function underneath. Of course, these approximations are going to get better as n gets larger. So as n goes to infinity, we should get closer and closer to the true value of these expressions. So the true value, sorry here, I need to erase again. The true value of the moment with respect to x and the true value of the moment with respect to y can be found with integrals as well. So apply a limit as n goes to infinity of this, and the actual moment with respect to x is going to be the integral of this expression here from a to b. We're going to have 1/2 rho of f of xi bar, the quantity squared. So f of x now, the quantity squared. And instead of a delta x, we'll have a dx. So there is the moment with respect to x. Whew. All right, then the moment with respect to y. Once again, we're going to apply a limit to this sum. The limit as n goes to infinity. It's going to turn it into an integral here. We're going to have the integral from a to b of rho times x times f of x. dx. There we go. So now we can actually find, now that we know the mass of the system, the complete mass of the system, we can take each of these expressions, divide them by this one, and we will find the actual centroid. And one of the nice things that's going to happen is if I take either this expression or this expression and I divide it here, you'll notice that this rho shows up in each one of these. So if I take the moment with respect to x divided by the mass, these rows are going to cancel each other out. And that's good. That's exactly what we should see, because it shouldn't matter whether the density of this expression is 10 or 10 million. The centroid isn't going to change because the mass on every side of it is going to stay the same. Okay, so the actual coordinates of the centroid. This is going to give you the y coordinate, so this one gives you the x coordinate. To get the x coordinate of the centroid is to take this integral divided by this integral. So we are going to have the integral from a to b of x times f of x divided by the integral of just f of x. And no, there's no more canceling that I can do here. The rows cancel each other out because they can be factored out of the integral. But this integral expression, these guys can't be canceled because multiplying by x inside the integrand is not the same as multiplying by x outside, right? This is actually changing the height of the graph at each point here now. So this is the simplest form that we can write the x bar in. Now for y bar, we'll take this guy and divide by that. Y bar can be found by taking this integral, the integral from a to b of 1/2 times f of x, the quantity squared dx, and dividing by the integral from a to b of just f of x dx. Once again, no canceling is going to occur here because the f of x is inside the integral, right? We have to actually take the integral first to find what each of these numbers is actually really equal to. Okay, so these are the actual calculations that we can do now to find the centroid of a general area under a curve. In the next video, we're going to see an example of this in progress.